Welcome to our video 2 of equation of motion case 3. So in this first we will have a recap of what we have discussed in video 1. So let's start with the question that we have. So in this question we are given that I will draw diagram first to explain you. We have an outer bob, we have an outer cup, and we have an inner cup. So in this question we have given that the fluid is placed between the between the two cup arrangement, and the outer cup is made to rotate with a constant angular velocity of omega naught. What really happens is that when this outer cup starts rotating, the torque is produced which causes momentum transfer in the fluid, and it is given in the question that that is equal to the product of torsion constant kt and angular displacement theta b. And the question, one thing is given that when this bob is rotated, we have an wire which is attached to it, which is attached to a fixed point. So and on the bob there we have a mirror which is used to calculate angular displacement by observing the deflection of light beam reflected from the mirror mounted from the bob. So when this bob starts rotating, it will initially rotate but come to an halt due to the wire which is fixed. That's the reason it will come to an halt after some time. So in this question we have to describe the viscosity of fluid. We have to derive an expression for it. So let's start with the boundary condition which is given in a question. So in this question the boundary condition 1 is at r is equal to kappa r, we know that v theta is equal to 0. And for second boundary condition at r is equal to r, v theta is equal to omega naught into r. And we also know that pressure will be a function of r and z. And for the velocity profile, we know that the v theta is going to be a function of r, and vr is equal to b0 and vz is equal to b0. Now using this information we are going to deduce our Navier-Stokes equation. So let's move on to the Navier-Stokes equation in cylindrical coordinate system. So this is our Navier-Stokes equation in cylindrical coordinate system. So here we are going to deduce our Navier-Stokes equation by the information that we have found over here. So let's start with it. We know that dou Vr by dou t is going to be 0 due to steady state. Here this term is also going to be 0 because we know that Vr is 0. Here it is 0 because we know Vr is 0. Here also it is 0. This term is going to be non-zero. Now next move on to this. This term is going to be non-zero because we know that pressure is a function of r and z. So dou p by dou r is not going to be 0. So moving over here, we know that Vr is 0, so this term is going to be 0. We know this term is also going to be 0 because we know Vr is 0. This term dou square Vr by dou z square is going to be 0. And we know that dou v theta by dou theta, we know that the v theta is a function of r. So dou v theta by dou theta is also going to be 0. and we don't have the gr in this direction, so this is also gonna be v0. So finally the our Navier-Stokes equation of cylindrical coordinate in our equation of motion comes out to be so minus p v square theta by r is equal to minus dou p by dou r. So this is our Navier-Stokes equation in our equation of motion. For similarly we are going to do for theta equation of motion and z equation of motion. So let's start with it. Let's start with theta equation of motion. So now we will have Navier-Stokes equation in theta equation of motion. So the Navier-Stokes equation comes out to be dou v theta by dou t plus Vr into dou v theta by dou r plus v theta by r into dou v theta by dou theta plus Vz dou v theta by dou z plus Vr v theta by r, which is equal to minus 1 by r dou p by dou theta plus mu dou by dou r plus 1 by r into r v theta plus 1 by r square dou square v theta dou theta square plus dou square v theta dou z square plus 2 by r square dou vr by dou theta plus rho g theta. So in this equation we know that first we have initially deduced that v theta is a function of r, vr is 0 and vz is 0. So we are going to use this information over here to deduce this information. We know this is steady state, so this is going to be 0 dou theta by dou r. We know that vr is 0, so this term is also going to be 0. We know that v theta is a function of r, so this term is also going to be 0. We know that v theta is a function of r again, so over here also this term is going to be 0 because it is given here dou v theta by dou z plus vr v theta by r. We know that vr is 0, so this is going to be 0. We know that pressure is a function of r and z, so we know that dp by dou theta is equal to be 0. Now coming over here, we know that d by dr plus into 1 by r into r v theta is not going to be non-zero plus 1 by r square dou square v theta by dou theta square. We know that v theta is a function of r, not function of theta, so this term is also going to be 0 plus dou square v theta by dou z square. For the similar reason this term is also going to be 0. Now moving on to this, we know Vr is 0, so it is going to be 0. We know that g is not in theta direction, so this is also going to be 0. So the final equation comes out to be 0 is equal to d by dr plus into 1 by r d by dr into r v theta. So this is our equation of theta equation of motion of Navier Stokes equation of cylinder. Now we will move on to the Z component of Navier-Stokes equation in cylindrical coordinate. So our equation over here is P into dou Vz by dou T plus Vr into dou Vz by dou R plus V theta into dou Vz by dou theta dou Vt plus Vz into dou Vz by dou Z, which is equal to minus dou P by dou Z plus mu 1 by R dou by dou R dou Vz by dou R plus 1 by R square dou square Vz by dou theta square plus dou square Vz by dou Z square plus rho Gz. We know that V theta is a function of R, Vr is 0 and Vz is 0, and pressure is a function of R and Z. Dou Vz by dou T is going to be 0 due to steady state condition. We know that dou Vz by dou R is also going to be 0 because we know that Vz is 0. So this term is also going to be 0. Dou Vz by dou theta is also going to be 0. V theta is 0. So this term is also going to be 0. We know that dou Vz by dou Z is also going to be 0 because we know that Vz is 0. Over here this term is non-zero because we know that P is a function of R and Z. So we know that this term is not going to be 0 plus mu 1 by R dou plus into dou by dou R into R dou Vz by dou R. This term is going to be 0 because we know that Vz is 0. So this is also going to be 0. Now moving on to the next term, we know that dou Vz by dou theta square is also going to be 0 because we know that Vz is a function of Vz is 0. So this is also going to be 0. This is also going to be 0 for the similar reason because Vz is 0. Rho Gz is non-zero because G is in the direction of Z. So the final equation comes out to be minus dou P by dou Z minus rho G. Till here we have deduced all the Navier-Stokes equation for given problem. For R component it is minus P V square theta by R into minus dou P by dou R. For theta component it is 0 is equal to d by dr into 1 by R into d by dr R V theta. For the Z component it is 0 is equal to minus dou P by dou Z minus Pg. So moving on to this equation, now we are going to, for the given component, we are going to use theta component. For the given question, we are going to use theta component for the given problem. So I will summarize it again. We have 9 Navier-Stokes equation, out of which we are using 3 for cylindrical coordinate, and out of 3 we have deduced it all the 3 questions. But looking at the requirement of our question, we are going. So for the given problem, we know that V theta is equal to, it is component of R, and Vr is equal to 0 and Vz is equal to 0. Vr is equal to 0 because it is symmetric due to symmetricity, and Vz is equal to 0 because we know it is a laminar incompressible flow. So let's start. So by using Navier-Stokes equation, we have deduced the equation in r, theta and z component. We will use for theta component, we will use the equation of theta component because we know for v, r component and z component the velocities are 0. So for theta component, the equation we have is theta is equal to d by dr into 1 by r d by dr into r v theta. Now we will integrate this equation. 0 is equal to d by dr into 1 by r into d by dr into r v theta. Now we will integrate this equation. By integrating this equation, we will get that 1 by r into d by dr r v theta, which will be equal to c1 constant. By integrating, we will get a constant, and after integrating this constant, we will get r v theta to half c1 r square plus c2. Dividing this whole equation by r, we will get half c1 r plus c2 by r. So this is the equation we have got by integrating our theta component, which we have deduced from Navier-Stokes equation. Now for this equation, we know we have two boundary conditions, boundary condition 1 and boundary condition 2. So the boundary condition 1 which we have is at r is equal to kappa r, v theta is equal to 0, and at r is equal to r, v theta is equal to omega naught r. So let's name this equation as 1 and this as 2 and this as 3. We will put equation number 1 and 2 in 3 to remove constants and obtain a equation of v theta. Now let's put equation number 1 in equation number 3. We will get that 0 is equal to half c1 kappa r plus c2 by kappa r, and let's name it as fourth equation. Now we will put equation number 2 in equation number 3. We will get omega naught r is equal to half c1 r plus c2 by r. Now we have two equations and two variables. Now we will solve both the equation to get a final answer. By solving this equation, we obtain that v theta is equal to omega naught r plus r by kappa r minus kappa r by small r divided by 1 minus kappa. So we had these two equations which we solved and obtained the value of C1 and C2. After obtaining the value of C1 and C2, we put the value of C1 and C2 in this equation to get a final equation, which is v theta is equal to omega naught r into r by kappa r minus kappa r by small r into divided by 1 by kappa minus kappa. So this is our final equation. In next video, we will solve the next steps of the problem. If you loved our video, please like it. Thank you.